All right, hi everybody. So today, 10:26, we are going to move on to the second half of 10.2, or 1.2, sorry, 2D motion. And we're kind of looking at the culmination of all 2D motion and projectile motion, this time in the two dimensions. So right now we've had projectile motion with horizontal, which is just the one dimension on how it's launched. Yes, eventually you get to two dimensions with the y-axis, but like upon launch, it's just one dimension. And technically, we've also looked at launching with the y-axis with objects falling and whatnot. So we're going to kind of look at how those things culminate together. So really the best way to kind of go about this is to look at an example question. So let's say that there is this nice wide open surface and there is a golf ball. That's a club. So club hits the golf ball, and if you've ever played golf, watched golf, whatever with golf, okay, hopefully you kind of understand that when this ball is hit, it is launched kind of up, okay, with some velocity. This is our launch velocity. That should sound familiar because we've had launch velocity with our horizontal axis. Okay, this time we have launch velocity, and this time there is some angle theta, or launch angle. Okay. Well, if we're doing a kind of a culmination of everything, there might be some things that kind of look familiar. Okay, so I'll try to point those out. I'm going to point those out as we go throughout this. But let's just kind of think about this. So this ball is going to go up in the air. Go boop, 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 up in the air. Reach some highest point, and then begin its way back down. Kind of spin this out. Boom. Lands over here. Well, let's kind of look at this in terms of our velocities and our acceleration, kind of like what we did with our horizontal velocity. Okay? So, this ball is launched up into the air. We'll kind of wait. Okay, so it's going up. Well, let's just kind of look at this point right here. Well, this point right here, it's going to have some velocity in the x. Also at this point, we're going to have some downward, or sorry, not, yeah, we're going to have downward acceleration. And also, we'll have upward velocity in the y. Now, the reason why we could say there's upward velocity in the y is because this object is gaining height. Anytime you've thrown an object, as long as it's at some angle, it has to rise. Well, in order for it to rise, there needs to be some vertical positive velocity. And acceleration is always pulling you down in the y-axis, so that one should make sense. Okay? And let's look at, let's say this point right here. Well, at this point, we still have some nice velocity in the x. We still have some nice acceleration in the y. And our velocity in the y is going to get a little smaller. Okay, this is not the greatest example, like picture-wise, but this gets the job done. Okay, because as this object goes up and up and up, okay, eventually acceleration overcomes your velocity. And we reach, let's say right here, the highest point. Sometimes referred to as the max height. Well, okay, now this goes back to remembering what we talked about with when you toss an object vertically upward. When you toss an object vertically upward, at the highest point, we always state that the velocity in the y is equal to 0. All right. But also at that point, we still have some velocity in the x, and we still have acceleration in the y. Then, as this object begins to move in the downward trajectory, there should be some similarities once again from before, in that now both your velocity and your acceleration both point down. It continues that way until we hit the ground. And as it goes down, velocity gets a little longer, a little faster. Your acceleration stays constant. Okay? So, a couple of things to keep similar. Well, x-axis, notice how I drew it all the same. Well, because remember, for what we're looking at in this, there's never any air resistance. Okay, so there's nothing to counteract the x-axis. It's always going at that same rate. So your velocity in the x-axis stays constant. So therefore, there is no acceleration in the x-axis. That's great news to hear. Okay, that's fantastic news. So, what that means, excuse me, sorry. What that means is, equation-wise, we still have this one and only equation for the x-axis. It's not changing, okay? That's kind of huge because that helps a lot. Now, there's one slight change we have to kind of make to this. Not really make, but I'm going to point out more this time. This time now factor, this is your total flight time. Okay? So, that time factor, the total flight time, that part stays the same. That part, it's like it was with horizontal, but we're just kind of denote it a little better this time. So x-axis kind of stays the same, which is fantastic. All right? Y-axis, though, gets a little weird. Okay? We kind of should look at the y-axis in two parts. Okay? Okay, part one, going up, part two, going down. Okay, that's kind of the general parts we should look at for this. The going up part and the going down part. Okay, so for going up, what I mean by that is when I look at from launch to max height. So velocity, final y equals 0. Okay? So for going up, we're looking from here to here, and then that should make sense for the going down. We look from here to here. Okay, so we kind of look at this in two separate parts. Okay, so if we look at it in the going up fashion, okay, if we look at it in the going up fashion, all three kinematic equations are viable. Okay. The difference, though, is that if for this particular case, T is the half flight time. Okay, I call it the T1 half. Basically stating that if we look at it from launch to the highest point, that is half of its flight. So therefore, if you double your half flight time, take it times 2, that gives you your total flight. So boom to boom, your half flight time. Okay? Delta Y gives max height. Okay, so like if I use the second equation or the third equation, okay, solving for delta Y would give me the maximum height of this launch, and then this should make sense that your final velocity in the Y should be 0, because remember at the highest point, okay, of this projectile, all the upward velocity is gone. So for a split second in time, there is nothing pushing it up anymore. All you have is things pulling it down in the y-axis. So at this exact moment, okay, there is no velocity in the y-axis. We call that our v final y. Okay, and then for the going down, all you kind of think about it is things reverse. What I mean by that is we now state that the v initial y is 0. Okay? You still have T1 half is still a thing. Okay, your delta y is now going from max heights to ground. So I'll actually write that down. Delta y going from max height to ground. Okay, so there is that change as well. Now, solving 2D projectiles really isn't much different. It's now just kind of, like I said, bringing everything together. And here, I'll give us hopefully some nice steps to always follow that kind of helps us figure this out. So, right away, step 1. Solve for, oopsies, that's 4, for v initial x, v initial y. So solve for your initial launch velocity x and the y. Okay, we think about this, usually things are launched some angle theta and your launch velocity v. Well, probably gonna have to use SOHCAHTOA. Okay. Step 2. Solve for T1 half. Okay. Solve for your half flight time. Sorry, lights turned off. Okay. So the reason why we want to solve for T1 half, okay, is because that lets us know exactly how high or the time it took this object to reach its maximum height, and then we can go from there. Step 3, really from there, you have everything you need. Okay,